And so in our last lecture, we'll finally speak about, we'll again speak about upper bounds for the sphere packing problem. So we already we've proven an upper bound for in dimension 2, and it was a sharp upper bound, which is very nice, and it's still a rare occasion when we have a sharp upper bound. And so today we'll speak about some more general methods, because the proof we had in dimension 2, it was very special and it worked only in that dimension. And then we will speak about sphere packing problem in dimensions 8 and 24, where we also have sharp upper bounds. And so as we already seen, so the proof of an upper bound can be very creative, and only our imagination is the limit. For example, the proof of Weierstrass for the packing of not only of regular disks, but for convex disks. It uses a lot of interesting techniques from, we used Euler's formula, we used different geometric lemmas, and finally everything came together and gave us the sharp result. And so in general, in geometric optimization problems, we have more, I would say, more industrial methods, which always give us some upper bounds, even though they are rarely sharp. And so here the idea comes from conic optimization. So maybe you had some experience with optimizing linear functionals over cones or over convex sets. Maybe you've heard of simplex method. And so this is a very nicely developed theory with many good results, useful techniques, and very important notion of duality. Because somehow convex optimization, it's not linear, but it's very close to being linear. And so duality makes sense. And now I will tell you about how these ideas can be applied to our situation, to the packing problems and problems of similar kind. And so let me start with an abstract definition. So what are copositive functions? So let us consider a metric space. And we will write by the support of this matrix rho. This would be the set of possible values of rho. And then we would say that a function f defined on this support and with complex values, it is copositive if the Holoving condition holds, if we know that the sum of such values is always non-negative for all finite subsets. Okay, so this is, I'll write a bit better. So this is small x, and this is a capital X. And this should be true for all finite subsets, capital X, of our metric space M. So here we fix a finite set, we consider all pairs of points in this finite set, and we compute such a sum. We evaluate f on the distance between these 2 points. And it turns out that, well, knowledge, if we could have, if for some metric space we would know, in some sense, this Cohn, or we would have a very easy test to test a function where it's belongs to this cone or not, then we would be able to solve many, many different geometric problems. And the difficulty is that for most interesting metric spaces, this cone turns out to be very complicated. Even in the sense of complexity theory, it's not an easy object to work with. And so there are many results of a type that if we have something like very good algorithm for working with this cone, then it would be too good and we could somehow solve all very difficult problems which are believed to be of high complexity. On the other hand, there is another cone of functions which is a bigger one. However, normally it has a simpler description. And so we would say that a function f, again from the support to the complex numbers, is positive definite.
We have a question.
Yes?
You wrote the sum of some complex values, and it's bigger or equal to 0, but we don't have...
Okay, yeah, okay, yes, okay, so then it has to be, okay, let's maybe write it this way, so it has to be a real number, and it has to be bigger than 0.
Oh, okay, thank you.
Can you read the rest of the definition, because I cannot quite read. What comes out after the formula?
For all subsets X, subset of M. For all subsets X of M.
Ah, okay. Okay, thank you.
For all, okay, I would say, okay, for all. For all finite subsets. Okay, so at the moment I will give you a class which is easy to describe, and then constructing things which are in here and not in there, it's a kind of complicated. Okay, for example, one example is that suppose that f is positive. Yeah. Okay, so now I will give a class of functions which are a bit less trivial, and and then finding something different becomes a challenge, or rather proving that it belongs to this set. So we consider sum of x, y belongs to x. So again, the function is positive definite if a similar condition holds. However, now what we do, we are also computing not just the sum, but a weighted sum. And this should be true for all finite subsets X. And all possible choices of coefficients Wx. And so now it's obvious that all definite functions, they're also, or all the positive definite functions, they're also copositive. So we'll see that positive definite functions they are inside, they're all copositive. And so now a typical situation is that the first cone is difficult to describe, and for this cone, for many interesting spaces, we actually have an effective description, and if our metric space also has some structure, then often the criterion for a function to be positive definite will come from the Fourier analysis on that metric space. For example, if it has a structure of a billion group or some nice group action on it. And so now, as you tell me about what are the interesting examples of functions like here, so I would maybe now write down a theory which tells us that knowing, somehow having a test for, or knowing good examples of functions here is in some sense equivalent to solving the type of problems we're interested in. And so here is the following, I would say, theorem, which is not any very interesting as a theorem, but maybe just as a shifting our, yes?
There is also intermediate notion where W are real, right?
Maybe, yeah, but that's not that useful. At least I don't find it that useful. And so, yeah, I mean, of course, there are many other things one could think about.
So this real is connected to convexity and complex.
Yeah, but this is one can think of it as a bit analogy with positive definite matrices. So, okay, so the theory is the following. So suppose that there exists a copositive function f such that it satisfies the following properties. So first, we normalize it so its value at 0 is 1. And then we assume that f of r is smaller or equal than minus 1 over n minus 1 for all r bigger or equal than certain fixed real number r0. So then we claim that then an r0 code in this metric space and an r0 code, it means a configuration of points inside of M such that the distance between two distinct points is bigger or equal than rho 0. So it's in some sense we can think of it as an analog of a packing problem. So then if this condition holds, then any rho 0 code in this metric space has at most capital N points. And N is the same that, okay, N from here. This is capital N. Yes? Sorry? What I've just told you, this is the exact definition.
Sorry, so there was a question from Kyiv.
No, okay, the definition is that this was the exact definition. So R0 code, it's a collection of points in our metric space such that distance between any two distinct points is at least R0.
Not 2R0.
And R0 is any number that we choose. So this is
We have a question as well, Maryna.
oh, yes, please.
To clarify the definition, so say if you have a pair of points on distance r0 and apply to it the definition of copositive, so there you wrote that the function will have negative values, is correct? For r0.
Sorry. Yes, so it's smaller or equal than minus 1 over n minus 1 for... So this is our assumption on function f. Yes, for all r bigger or equal than...
if your set X consists of 2 points on distance R0, then it seems that the value of the sum in the definition of copositive will be negative, no?
Yeah, but okay, but that's exactly, you are just stepping on the proof of the theorem, right? So this is.
I see, because of X equal to Y.
Okay, so this is the theorem, right? So suppose that there exists a copositive function, then this condition has to be true, and then how we prove it is actually exactly what you have told. So this is kind of an.
We are doing well at work.
Okay, so let X is a subset of M, be an R0 code. So now, okay, let's prove the theorem, and suppose that we do have an R0 code in our space. Now I want to prove that it cannot, if we have somehow constructed a function like this and we were able to prove that it is indeed a copositive function, then we would know, and we assume that we would be able to bound the number of points in this R0 code, and we do it exactly in the way that was suggested. So we know, okay, so this is true because f is copositive. And so now on the other hand, what we can write is the following thing. Okay, so now we split our sum into two parts. So here we're summing over all pairs, and here first we sum over the diagonal pairs, and here pairs which are where 2 points are distinct. And so now we take into account the first two assumptions we have made on function f, and we know that this term is just equals to the cardinality of x, and this term is bounded by the following number, so this would be the cardinality of x times cardinality of x minus 1 times 1 over n minus 1. And now what we have to do, we have to compare these two conditions. And so if we compare them, we can see that they imply that the cardinality of x has to be smaller or equal than n, and this finishes the proof.
Maryna, sorry, but this f must be monotone then if you have such a, because you have here r, and in this case.
But why should it be? I don't think why it should be monotone.
No, no monotonicity from f.
Not assumed, and I don't think it. I think if it does not follow from being.
How do you obtain this inequality? The last one.
Yeah, but this is true for all r bigger or equal than r0.
Okay, thank you.
Okay, but this does not seem like a very exciting theorem, right? So we made a definition, and it's in some sense it's a consequence of our definitions. But what we can see from here is, okay, if we have an effective description of Cohn of copositive functions, then, for example, a packing problem becomes kind of easy for us. But of course, here there is a bit of I'm lying. Okay, what I'm hiding from you is that how to prove that something is copositive. So we are kind of replaced one problem by another problem, and it seems like we have done nothing much. However, in the theorem that I have already erased tragically, so we can replace the word copositive by positive definite, because this is a subset. And then this actually becomes a very powerful tool. And in many situations, this is somehow the best we have, and coming up with other strategies seems difficult. And so this is what we are going to do now. Now we are going to replace this idea of instead of considering the Cohn of copositive functions, we will look closer in the Cohn of positive definite functions. And so now let's apply it to some examples. And so this idea, it works not only for Euclidean spaces, but it can be applied to any metric spaces, and historically it was applied, and the method, at least in the form that I presented it to you, it's better, much better designed for compact spaces, because here we got a number of, like bound for the number of elements in the code. But in Euclidean space, we can have infinitely many points, so the whole strategy would have to be modified a little bit, and I will speak about it in a few minutes. But before, I want to make an example, and to my knowledge, this is the first, historically, this was the first example where this technique was used. And so let's consider the following metric space. So the metric space would be the Hamming space, so our set of points, they are the vectors in n-dimensional vector space over the finite field with two elements. So, and the distance would be the Hamming distance. And so I'll just recall that the Hamming distance of x and y are two vectors in this space. So there are two sequences of n symbols of zeros and ones, and the Hamming distance, would be just the number of positions where L1, yes, so xi is not equal to yi, yes. And so this it's not difficult to verify that this distance that satisfies all the necessary axioms of the distance, like triangle inequality, and yeah, so it's a useful object. And so now let's think about like what would be the positive definite functions on this metric space. And so here, so first let's introduce a bit more structure. As I told you, that somehow more structure usually lets us to answer the question better. So first let's introduce the scalar product in a standard way. So the scalar product would be also element of F2. And so let's fix some element in our vector space, and let's consider a function like this. So it would be e to the pi x times y. And so then, because actually this number is well defined, even if the scalar product is just an element of F2 because of the periodicity of this, of the e to the pi something. And so now, okay, let's compute a sum like this. So we suppose that we...
Sorry, Maryna, but you could do the same in just unit cube in L2 and obtain the same result with usual scalar product, right?
Yes.
Mm-hmm.
So now let x be a finite set. So we have okay, and so now kind of an interesting, okay, so sorry, so this should be, okay. And now an interesting thing happens. It's that now we can rewrite this double sum as an absolute value squared of a single sum. And this is always a real and non-negative number. Okay, so this is, it seems like we have constructed this positive definite function. There is only one problem right now, is that this function is not a function of distance between x1 and x2. However, what we can do, we can now average this function by the action of symmetric group, and then what we will get, actually a function of the distance, and this function, it would have a special name, or it's easily described in terms of special polynomials called Kravchuk polynomials. So I will somehow skip the details of this computation. So we have the Kravchuk polynomials. And they are defined in a following way. So it's a k, so it depends on k, d, and n, and it's a function like this. Okay, so probably I guess here should be maybe r, so just to be consistent with my previous notations. Okay, so here k, it's a parameter, so we have n constructed n plus 1 such functions for fixed dimension n, and r, it is the distance. And then this polynomial, this function, it becomes a positive definite function on the Hamming space for each k in the range. And so maybe the proof of this lemma I will leave to you as an exercise. And so the hint for the exercise is to show that Kravchuk polynomial, it's an average of a function like this, where we have for y, so this is the action of symmetric group, and under the action of symmetric group, each orbit is just vectors of given weight, or vectors with a fixed distance to the zero.
Sorry, what is the formulation of lemma? Because this is just definition.
The Kravchuk polynomial, okay, yes. Okay, R positive, yes. Okay, so Kravchuk polynomials are positive definite. With respect to the this matrix, the Hamming space. Yeah, maybe last thing I would like to mention that Kravchuk was a mathematician and who lived in Kyiv, and his monument is near the Kyiv Polytechnical University. So if you have time today, it's actually not that far away from here. So.
A bit far.
Yeah, not for Warsaw.
The question?
We have a question.
Yes, so parameter k is a number of ones in your y, or
sorry?
K?
Yes. So you choose like k somehow corresponds to the number of non-zero coordinates in a vector y, and then we have to take a sum over all such vectors, and then what we will get would be this polynomial, and this polynomial will depend not on x, but only on the number of non-zero vectors in x, which is somehow is a bit of maybe a bit of work to show that, but somehow when we symmetrize over y, a nice thing happens, which is maybe not that miraculous if you know how group actions work, then the thing becomes also symmetric for in x.
So sorry, what is connected with Kravchuk
Yes,
near
you have another
Polytechnical University? The flat where he lived, or what? You mean?
Oof, okay, so maybe I'm not. I thought that he worked there, or that's why he.
Maryna, we do have one more question.
Yes.
Can this be generalized to other values of p other than 2?
Yeah, I guess so, but yeah, I mean, then I'm not sure. Okay, then probably lemma would have to be modified. So I'm sure that somehow the yeah. So we would still, I think, we would still have a nice description for positive definite functions also for other p, but I imagine that the polynomial has to be modified in that case. And yeah.
Sorry, just to clarify, you fix k and n, and each of them is positive definite. Is that right?
Yes. Okay. So n is really the n that comes from our space.
Okay.
And like this is the variable which is the value of the matrix, and then k is the only free parameter which we have. So here we have constructed k different positive definite functions. Sorry, not k. So n plus 1 different positive definite functions. Okay, and so now how this, now for example, if we use this knowledge that we have about positive definite functions on Hamming space, actually we can prove optimality of some famous codes, for example, of a Hamming code. So there is a famous Hamming '84 code. And so, okay, so maybe I can, so I will not, so it's a linear code, and it's given by this matrix, which probably, there is no much benefit for me writing this matrix for you. But okay, but I have it on my slide, so I will do it anyways. So there is a certain 4 by 8 matrix, and it defines a 4-dimensional linear space in 8-dimensional space over vector space over F2. So it would be is a subspace of dimension 4. And what is nice, so this is the generating matrix for that subspace. And what's a nice property for this subspace is that the minimal Hamming distance between two elements in this subspace is 4. And the number of elements is 16 because it's a 4-dimensional space over F2. And so now the theorem, which we can prove with help of the previous theorem I've showed you, is the following. So let X would be a code of distance then its size is at most 16, which is the size of Hamming code. And so the proof is, the scheme of the proof is very simple. So here we will construct the function which satisfies our previous theorem. So we consider the following function. So we would want like f of t. Okay, so this would be this function. Okay, why is it? Okay, hope I'm not making a mistake here. So we can take an explicit, certain explicit polynomials, and so it will somehow, here we can see that the conditions of our theorem would be correct because it's somehow normalized so that it is, it should be, no, it's not 1 at 1, but okay, it can be normalized so that it is 1 at 1. And then it becomes negative between 4 and 8, but then in our support of our measure, we don't have elements of size bigger than 8. So, and now what is somehow magically work is that we somehow constructed this from our knowledge about the support, and now we can write this polynomial as a combination of Kravchuk polynomials. And this combination turns out to be positive. So all the coefficients that we see here, they are all non-negative. So there are some which are 0, and there are some which are positive. And so then we know that this function is positive definite, and therefore we can apply previous theorem. Okay, so now if there is no questions for the Hamming space, yes?
So the existence of such code of such a space is specific to dimension 8, or is there a general construction?
Yes, okay. I don't understand what you mean such. There are codes in different dimensions, and yeah, Hamming spaces, Hamming code is quite unique. For example, so maybe you can say like which properties of Hamming code you are willing to generalize to other spaces.
Basically, having some special subspace with this property, the distance between any two points is at least half of the dimension.
Yeah, so this is just the definition of what's called the linear code, and I mean, okay, so it's all this game between parameters. So of course, I know that Hamming space is very special, so we can see it from this theorem. It's kind of one of these very rare perfect codes. But yeah, but what is the threshold? Somehow it's all somehow known to mankind. But here I'm not ready to, yeah. So the fact that it's half of dimension and also half of size, yeah, maybe this is not. Here I'm not that confident that this is really the key thing. So. The whole field of coding theory is finding out, of course, like what are the optimal relations between the parameters, such as dimension and distance. And I know that this code is optimal, but the condition which you said, I'm not sure, like, where is it? Is it an impossible domain? Is it on the edge? Or is it just like a regular thing? This I would have to think a bit more about.
One more question from Kyiv. So in the statement of previous theorem, there was a condition on the bound of f of r by a negative number from above. But here, if we take t equals 4, which we said that the distance is at least 4, then f of 4 is 0.
Yes.
Is that okay?
Okay, yeah, so maybe, okay, okay, it could happen that there is, it could happen that there is actually a, because in my original slide, what is written is something like this. And I forgot to write what is F0, so maybe this is somehow morally correct, but needs more polishing, I would say.
Okay, thank you.
More questions? No?
Okay, so now let's and the next thing that I would like to do is to show how this method can be adapted for the packings in Euclidean space. And so this was done for, okay, there have been several, actually there are more works on this, but my favorite adaptation is by Cohn and Elkies. So they formulated the following version of this theorem. So suppose that there exists a Schwarz function f from the n-dimensional Euclidean space to real numbers, and we suppose that this function satisfies the following conditions. So first, f of x is non-negative for at all points that have lengths bigger than fixed number R0, then the Fourier transform of x, which is, so its Fourier transform is well defined because our function is a Schwarz function, and Fourier transform is also a Schwarz function.
Sorry, what is a Schwarz function?
So a Schwarz function, it's a function on Euclidean space, which is infinitely smooth. And the function itself and all its derivatives, they decay faster than any inverse power of distance to the origin.
Basic function, right?
Sorry?
Basic function is distributed.
I know. I know this under the name Schwarz function. I don't. So
thank you.
That's a terminology I am familiar with. So so sometimes they also refer to maybe test functions. So yeah. So like this not nice smooth functions with infinitely many derivatives and nice decay in all of those derivatives. So, and so we also request that the Fourier transform of this function is non-negative at all points of Euclidean space, and we normalize the function in such a way that the value function at 0 is the same as the value of its Fourier transform at 0. And is 1. And then if we are able to produce a function like this, then we claim that each periodic configuration X in Euclidean space such that the distance between 2 points is bigger or equal than R0, so each periodic configuration which is 0 and also an R0 code. So then this periodic configuration has has point density at most 1. And so in all our previous lectures, we always spoke about density of a sphere packing, but now it's somehow just the theorem looks nicer. We don't include any volumes of balls here. If we speak not about the density of a packing, but rather density of point centers, and here it means that this is the number of point centers per unit of volume. And then two things are connected by a linear factor, which is just the volume of a ball of radius r0 divided by 2. Yes? So I mean that there exists lattice, some lattice, such that our... So the question is, what is a periodic configuration? Yeah. And periodic configuration means that there exists some lattice in Euclidean space, such that our configuration is invariant with respect to the shift for this lattice.
Okay, thank you. And could you remind this point density at most 1 means what exactly?
Okay, so point density, it means that would be the, okay, so point density so this is would be the, again, like some limit or limit supremum of the number of points of our X intersected with a big ball. Divided by the volume of big ball. So the number of points per unit of volume on average. And so I will not go today for the somehow reasons of time. I will not go into the proof of this theorem, but the proof of the theorem is rather simple. If you are interested, I suggest just looking at the original paper of Cohn-Elkies. I think it's also very pedagogical, and yeah. So the proof is a bit similar to the trick we have done before with Hamming spaces. And so now what is interesting are what are the consequences of this theorem. So what Cohn-Elkies have done in their 2003 paper is that they somehow used this principle and applied it to dimensions from 3 to, I think, 36. And so there they searched for a suitable function f numerically. So for each dimension, they would find a function which satisfies this condition for R0 as big as possible. And they searched for a function in the following form. So they searched for a function as a polynomial times the Gaussian. So then the Fourier transform of such function is also polynomial times Gaussian, and they are related by a certain linear transformation with known matrix. So this becomes a computational optimization problem. And so they numerically found some results, and in most dimensions this would be some upper bound, and typically they would be better than previously known upper bounds. But they would also be quite far away from the densities of known configurations. And in two dimensions, however, in 2 dimensions, the situation was very different. So So in dimension 8, the upper bound that they were able to prove by numerical method was very, very close to the density of a known configuration. So they have proven that if there is something which is better than E8 lattice, then it will be only this much better. And if there is something better than the Leech lattice, which exists in dimension 24, then it's only this much better. And actually, these are results from 2003, and then subsequently they were improved. And so I think here at some point, the number of zeros was like 60 zeros and then some significant number. So it was pretty clear that the function like this, it does exist. There exists some explicit functions, one function for dimension 8, one function for dimension 24. And it also seems that this function is not of the form Gaussian times a polynomial, but it is something else. And so maybe I would want to say that this is my contribution to the field, was to find the exact shape of this function for dimension 8. And then okay, so what I was able to prove is that there exists a radial Schwarz function FE8 from 8-dimensional space to real numbers such that FE8 of x is smaller or equal than 0 for all points of distance bigger than square root of 2, because this is the optimal parameter we can have for the lattice E8, and its Fourier transform is non-negative, so and also it's normalized in a way that we require in the theorem of Cohn-Elkies. And then same year, collaborating together with, so same year together with Henry Cohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko. We were able to construct such a function for E8 lattice, for the Leech lattice. Okay, and so I have and so maybe one thing I was also to say that because these functions, they kind of magically prove a difficult geometric theorem for us. So as I remember, Stephen Miller, he suggested naming them the magic functions. So, and so I have 3 more minutes left, so maybe I can tell you a little bit about how the idea how to construct functions like this. And then maybe Danilo will speak a bit more in his talk. And so, so what are the clues how to find such functions? So let me make a sketch of a plot of this function for you, for example, for E8. So okay, I'll make actually maybe the plot actually works for both of them. Plot of the magic function. Okay. So the function, of course, is fast decaying, and I will not grow it to be fast decaying, so we normalized our function, so it is 1 at point 1, and we know that E8 lattice has vectors of lengths that are square roots of even integers. And so the function, so this would be, okay, so let's write it, absolute value of point in Euclidean space squared, and here we would have the value of the function. And the function, it would have sign change at the first element in our support for the, let's say, distance, for the Euclidean distance on E8 lattice, and then it would have double zeros at all other square roots of even integers. And something like this, we already seen it in a similar situation as we considered the Hamming code. So there are also somehow the zeros of this special function that provided optimal proof for us. Provide the proof for us, they kind of really depended on the spectrum of our code. And if we look at the Fourier transform, the Fourier transform had similar structure. So we also had 1 at 1 because it's our normalization. But now at all square roots of even integers, we would have double roots. And so now, but now it turns out that this is not a coincidence. It's actually an exact result of optimality in the Cohn-Elkies theorem. And somehow another more interesting fact is that it turns out that only this information, the fact that function is 1 here and its Fourier transform is 1 here, and then the function vanishes at all these points, and its Fourier transform vanishes at all these points, it was actually sufficient to recover the function uniquely, because of the Fourier interpolation formula that we were able to prove. So we have seen that for any Schwarz function, if we know its values at all these points and the values of its Fourier transform at all these points, then we would be able to reconstruct the function in a unique way. And so this is something, this kind of phenomena, which Danilo Radchenko will speak about only, like not only for, because this set of nodes of points where we compute function its Fourier transform, it came from a geometric optimization problem, and this was the motivation. But Danilo will speak about another interesting example, which turns out the same is true for example, roots of L functions. So yeah, so I hope that he will be able to cover somehow both, to speak more on this topic and also to cover his result, which is very exciting. So I think I'm now out of time, so thank you very much.